Blaise Pascal. I want you to look at the dates when he was alive. He was actually an integral part of the development of computers. Look at that. In the 1600s, this guy figured out a language of zeros and ones that could be used as a binary code. That's how great this was at patterns. He was excellent at it. So today when we go through some of these things, what we have to realize is this guy spotted patterns from a mile off. You know, he was just one of those people, the irritating ones where their hand goes up right away when you ask them about a pattern because they just see it, you know. But very prolific. He wrote a ton, and not just in mathematics, but in other fields as well. Things that they really couldn't make happen at the time. I mean, imagine this. He's writing binary code in the 1600s. There's no computers in the 1600s, for goodness sake. They're lucky to get enough electricity to make a light bulb go on, you know. So he was really, really good at patterns, and that's what we'll see today. There's patterns within patterns that he found. So our objectives are, we're going to expand a binomial using Pascal's triangle and use what's called the binomial theorem. So what does that do? Well, the binomials that we're going to be talking about will be trying to figure out what would that be? What would the binomial x plus 3 to the 5th power, what would the answer be? Now, we know how to make it happen. We'd have to write out x plus 3 times x plus 3 times x plus 3 times x plus 3 times x plus 3, and that would not be fun. Because we'd have to take two of them and multiply them together, maybe do that 2 times. There's distribution all over the place. Chances are pretty good we're going to mess up. I mean, there's a lot to keep track of when you're going to raise something to the 5th power, but not with Pascal's formula. With his noticing the formula that we're going to create, this will go really quickly. It won't be bad at all. So Pascal, we're going to start by talking about his little triangle. And Pascal did this. He said, all right, if I'm going to use some numbers here and start a triangle, I'm just going to make a little triangle of ones at the top. So 1, 1, and 1, making the vertices of my triangle. Now, I wonder what would happen if I always start with 1 and end with 1, but to get the stuff that's in between, I go to the row above and I add those two numbers together. So 1 plus 1 gives me 2. And then I start with a 1 again, but now I add these two numbers together, add these two numbers together, and I end with a 1. 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, etc. Doesn't look much like a 5. And they called that Pascal's triangle. Now, in and of itself, there's nothing remarkable about that. You could say, hey, grade school, you could do that, figure out a pattern. But here's where he recognized it. He said, you know what, I've seen these numbers before. This is what you get from 0, choose 0. That's combinatorics. So juniors, you have seen this before back in Common Stats. 9th and 10th graders, you're going to have to hang on a couple of sections so that I can introduce you to combinatorics. And then he said this one would be 1, choose 0, and 1, choose 1. This one would be 2, choose 0, 2, choose 1, and 2, choose 2. And it works every doggone every time. So the combinatorics that he saw connected these two things together. Now the one glitch with this, and this is usually the part that most Algebra 2 students have trouble with, Pascal was a computer guy. He didn't start counting with 1. What did he start counting with? 0. So this row up here is called row 0. Then we've got row 1, row 2, etc. So usually it's not the use of Pascal's triangle that people have trouble with. It's just remembering, okay, he's a computer guy. He's going to start counting with 0. And that's what he did. So Pascal's triangle is not something that's going to be given to you for the test. It's something you could recreate really pretty quickly. I mean, we're not going to take you down into any of the low powers to use here. I should say high powers, like to the 8th power or anything like that. But all you do is start with your 3 ones, and then realize I'm going to start with 1, end with 1, add the 2 numbers that are above it. And I would say, yeah, probably 5th or 6th power will be as far as we'll ever go with any of this. Because these numbers are not just significant for combinatorics, they're significant when we want to expand binomials, when we want to multiply things out that are in that binomial form. So, next page says, our essential understanding is patterns everywhere. We can use a pattern of coefficients. Remember, those are the numbers in front of the variable things? A pattern of coefficients and the pattern, oh my gosh, that's really scary looking right there, isn't it? A sub n minus 1, b, a sub n minus 2, b squared. Hang in there for that one, I'm going to talk you through it. And we are going to use that to write this expansion, a plus b to the nth power. So let me explain what they're trying to tell us. What they're trying to say is, if you want to take a plus b to the nth power, pretty obviously, at some point, you're going to get a to the n. Well, that'll be your highest power of a. So you're going to start with your highest power of a. Then you're going to go 1 down. And then you'll go 1 more down, and 1 more down, and you're just going to put it in standard form for the a's. But the b's, it says, those are going to start low, because really this would be like b to the 0. B to the 0 is 1, it just disappears. B to the 0, b to the first, b squared, b to the third, and you would just keep going with that b pattern. So what this is supposed to show us, which is, it always happens, somebody doesn't do this assignment tonight, and then they come back 2 days from now, and they go to do this assignment and say, I knew how to do this when we were doing this in class, but now I've forgotten. So let's write this down. A's go high to low. So whatever that first term is, you start with the highest power and you work your way down. B's go low to high. B's go low to high. Now remember, he's a computer guy. What did he start counting with? 0. So don't forget that. We're going to use that 0 power first. And then they mention a little bit later here. In fact, let me connect that up before I write the last thing down. It says, if we wanted to expand a plus b to the third using the distributive property, this is what we would do. It's what we've done in the past. A plus b times a plus b times a plus b. We multiply 2 of them together with FOIL. We combine like terms. Then we distribute a 1 more time, and we distribute b 1 more time. And this is what we would get. Now, with what we have already, we could already do a to the third, a squared, a to the first, a to the 0. We could already do the b's. B to the 0, b to the first, b squared, b to the third. But where did this 3 and this 3 come from? Well, it's not just the 3 and the 3. It's 1, 3, 3, 1. This is row 3. These are the numbers for the coefficients in that expansion. So imagine, no computers back then, lots of old textbooks where people just wrote stuff in. And this guy says, wait a minute, this is combinatorics, and it's also expansions of binomials. My head would burst open. So that's what he saw. The A's go high to low, the B's go low to high, and we're going to call these the C's for coefficient from Pascal's triangle. Or on the first day back after break, apparently it's a triangle. That's going to expand these ones so that we don't have to write them all out. Keep going. So a plus b to the first power, the 1's not doing anything. That's just going to be a plus b. But now I'm going to look at that a little differently. I want to think, well, what's the number in front of both of those? 1 and 1. Row 1, 1 and 1. A plus b squared. All right, well, that's going to have a squared, a to the first, a to the 0, which I'm not going to write down because a to the 0 is 1, b to the 0, b to the first, b squared. Now I need to know what numbers are going to go there. Well, that was 2, so I need row 2, which is 1, 2, 1. Now I just need to figure out what sign is going to be in there. Well, it's a plus b. And it's going to be a plus b times a plus b. There's no negatives that are ever going to show up in this. So it's really a squared plus 2ab plus b squared. Go to a plus b to the third. A's high to low. A to the third, a squared, a to the first, a to the 0, which again is just 1, so I'm not going to bother writing it down. B to the 0, b to the first, b squared. I didn't leave myself enough room. I write too big. And then b to the third. Now I grab my numbers. Row 3. Row 3. 1, 3, 3, 1. And then all I have to do is put my pluses in. And that's my formula for expanding a plus b to the third. A plus b to the fourth. I'm going to write down here this time. A to the fourth, a to the third. A squared, a to the first, a to the 0. Just 1, it's not going to help. B, low to high. B to the 0, not going to write it down. B to the first, b to the second, b to the third, b to the fourth. Now keep in mind, this power is what we end with. Some people will forget to put that last term on there, but remember, the power has to be 4 in that last one. Row 4, come over here. 3, 4. 1, 4, 6, 4, 1. And then we put our pluses in between each one of those terms. That's how this formula always works. A's, high to low. B's, low to high. Pascal's triangle for the C's. And then we plug in whatever information we get. So these expansions are things that we did before, but we didn't know there was a formula that would help us out with the higher powers, which is okay because now we know 2 ways to go about this. But really, if you have a power higher than 3, you're not going to want to multiply this stuff out. You're going to want to use our new formula. So this 1 right at the top comes from a plus b to the 0. Computer guy, it starts with 0. Anything to the 0 power is 1. 1 a to the first and 1 b to the first, that's a plus b to the first power. And notice over there in Pascal's, it's a 1 and a 1. Then we have a plus b squared. Pascal's triangle says that's 1, a 2, and a 1 for those coefficients. That is. And then we have it to the third power. That's our 1, 3, 3, 1 from row 3. And the fourth power, 1, 4, 6, 4, 1. Did anybody notice there are lots of patterns within Pascal's triangle that are useful in other fields as well? Did anybody notice any other patterns inside the triangle that we have so far? Abby, what did you see? Yeah, it's symmetry. Yeah, symmetry. She said it mirrors itself. That's exactly what it does. You've got this 10 here that they both have, and then it works its way backwards. Here the 6 was right in the middle, and then at 4 1s its way back out. There are tons of different patterns within Pascal's triangle that are used in lots of fields of mathematics. So if you're working through it and you're going, oh, I see another pattern, good for you, because there are lots of them that are going to help us out. So using only the coefficients, we match those numbers in Pascal's triangle to get the formula. We want a formula. And then what we're going to do is figure out where do we go from here. So what I first want you to do is go back to that front page, and I want you to generate the next 2 rows of Pascal's triangle. So go back here. Oh, come on. And go ahead and get the next 2 rows. And realize this is just addition, but we are going to be using the calculators to do some of the math with this later, involving powers. So if you have a calculator, please take that out. Otherwise, I'll grab a couple here. How many people are going to need them? Anybody else realize you don't have a calculator with you? No? Okay, keep going. We'll check in and make sure everybody gets right. And do the next 2 rows. Call on people to tell me what they got for row 9 and row 10. So if you want a chicken wing, elbow partner here and check in and make sure your answers are correct, you do that. Just the next 2. Some people, just a few people are still finishing up, but I'm going to go ahead and start on row 9 here to make sure we all have that correct before we go any further. So, let's see.
I agree.
Facing that way. So, Brandon, what'd you get for row 9?
1. Should I just do them all?
Please.
All right. 1, 9, 36, 84, 126, 126.
Hang on a second. 1, 9, 36, 84.
126, 126, 84, 36, 9.
Did you do the whole row, Brandon, or did you get halfway and then go, wait a minute, start to do that symmetry thing? Yeah. Some of you didn't. Some of you were like, you know what, I'm just going to go ahead and do this whole thing because I'm not exactly sure where that break is. But when you get to the 126 and the next one you do is 126, you should say to yourself, oh, that's got to be where it flips over. That's the whole thing. All right, so row 10. Once we have those, Lainey, what'd you get for row 10?
1, 10, 45, 120, 210, 252, 210, 120, 45, 10.
You can always look at it up here.
I know, you were crude.
Oh, that's all right. Because I knew once she hit the 252, I was just using symmetry to get the other one back on there anyway. But thank you, lady. So we're not going to get this far on the problems. We're not going to give you something to the 10th power. We're just not. Most of the time we stick to about row 5 and above. You know, something that's useful for what we would be working on right now. And this is one of those things that over the years, there's actually been one that showed up on the MCAs one time. You know, we got done with the MCAs and the kids had said, there was something in there, said something about Pascal, and we had skipped it because it wasn't something that was supposed to be showing up on the MCAs. But every once in a while, they'll throw one of them on there just to see, are you getting taught this stuff? So we want to make sure you've got it. All right. So once we add those 2 rows, we have more than enough of what we need in order to do the expansions that we need to do.
When we do the powers and stuff, they'll all be whole numbers. All numbers.
Yes, we're not going to ever put, I don't even know if you'll see that in calculus. They might not even use negatives or anything like that until you get into the calculus classes. So yeah, for this class, just the whole numbers, yeah. Alrighty, so this says, we're going to switch it up on you. Not just the A and B stuff after this one. They want us to get the pattern down first, and then they're going to take away the A and the B and start giving us some X's and other things. So I look at this and I think, oh, no biggie. A's high to low. It is an A. That's the first term. So A to the 6th, A to the 5th, A to the 4th, A to the 3rd, A to the 2nd, A to the 1st, and A to the 0 again. I'm not even going to bother writing A to the 0 down. You know what? Maybe I ought to at least once. You've got 1 in your notes. Try to put it all together and say, where did that 1 go? Well, it was to the 0 power. So A's are high to low. What are B's? Low to high, and we start counting with 0. B to the 0, B to the 1st, B to the 2nd, B to the 3rd, B to the 4th, B to the 5th, B to the 6th. Where do we get the C's? We did A's high to low, we did B's low to high. Where do we get the C's? Pascals, what row should we look at? Row 6. 0, 1, 2, 3, 4, 5. Oops. Flip back to the front. I'll just go ahead and put it up here. We might need to begin. Writing a 5 from above is not a skill I possess. So 1, 6, 15, 20, 15, 6, 1. We write out A plus B times 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 A plus B. Is there any chance that subtraction is going to show up in that problem? But you should be thinking, as a curious math student, what it does. I mean, what this one's all pluses, and that's all we've been doing so far. But what if it's A minus B? Then what do we do? It's really easy. If it's a minus, the pattern always does this. The first term is always positive, then it's negative, positive, negative, positive, negative, positive, negative, forever. That's always the pattern. The first term is always positive. If there's a minus between your 2 terms, then you just say it's positive, negative, positive, negative, positive, negative. Always oscillates back and forth, positive and negative. So the last thing we want to do with this one is pretty it up, which means simplify it a little bit. We've got some stuff to the 0 power we don't need up there, and we have some 1s we don't need. So we don't need this 1. We need an A to the 6th. We don't need this 1. That'll be A to the 6th. Plus 6 A to the 5th B. Don't need that power of 1 on there. Plus 15 A to the 4th B squared. Plus 120. Just 20. Look at at that, it didn't take in line. There. A cubed B cubed plus 15 A squared B to the fourth plus 6A B to the fifth plus B to the sixth. And now it's all simplified. The extra ones that we didn't need, the A to the 0, A to the 0 that we didn't need, those are gone. So I warned you, not always going to be A and B. They're going to start actually putting numbers and different variables in there, but this is the pattern we follow. A is the first term, always high to low. B is always the second term, always low to high. C's right here, Pascal's triangle. And then we just check to see, did it have subtraction? If it did, we're going to do plus, minus, plus, minus, minus. Patterns within patterns. All right. Next up, theorem for binomial expansions. I'm going to uncover this. Don't run screaming and crying from the room. First of all, there's no crying in math. You know that. It's called the binomial theorem. But look at that. That is a monster. But it says exactly what we've been doing in the language of math. It says, start with your A's with their highest power and work it down by 1 each time. That's exactly what we've been doing. Then it says, take your B's and start with B to the 0. It's not even going to be here. B to the first, B to the second, B to the third, etc. All the way up to B to the n. And this P, what do you think a capital P stands for in what we're doing today? Pascal's triangle. So you go to Pascal's triangle and you get the numbers that go in front for the coefficients. So it looks really scary, but it's exactly what we've been doing. It's nothing new. So now, they mentioned, when you use the binomial theorem and you want to expand x minus 2 to the fourth, you have A stand for x. And here's where I differ from the book. B, I would just use 2. And then at the end, I would put my signs in as positive, negative, positive, negative. I wouldn't even bother putting the negative in there. You can. Doesn't make any difference. You can leave it just as it is in your notes. But I always do that as my last step anyway. So that just makes sense to me not to even bother with the negative 2 when you're raising powers. And the other reason is because when we take negatives to a power, we tend to make mistakes. So it's easier to just remember the pattern. If we want to expand this one, A would equal 3x and B would equal 2. And then again, we'd have to go through and use the plus, minus, plus, minus. But here's the key. Don't forget that when we have to raise 3x, all of it to the fourth power, that means not just the x is going to get the fourth power, but the 3 is going to get it too. And that's where calculators come in handy for this stuff, because sometimes we do have big numbers that we have to find. So down here, we have a little 3x minus 2 to the fifth, and we want to expand that. So the first thing I do is look at this and realize, well, this is really like a minus b to the fifth, where a is 3x and b is 2. And then I remember my ABCs of binomial expansion. The A's go out. A's go which way? High to low. So 3x to the fifth, 3x to the fourth. I leave myself a tremendous amount of space because I don't want my terms to get mixed up. And if you do that, and you just go slowly and carefully, everything works out well. 3x to the third, 3x squared, 3x to the first, and 3x to the 0, which I'm not even going to write down. There's my A, high, low, 5, 4, 3, 2, 1. What's next? How do you do the B's? Low to high. Now my B value is a 2. So I'll have 2 to the 0, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, and 2 to the fifth. ABCs, we have A and B done. Where do we get C? Pascal's, so we need row 5. 0, 1, 2, 3, 4, 5. 1, 5, 10, 10, 5, 1. all pluses or plus minus plus minus? Plus minus plus minus. This one's subtraction. So this one's positive, negative, positive, negative, positive, negative. And now comes the part where a lot of people will just grab their calculator to have the calculator do the math. Here's why. You have to follow the order of operations, which means you have to do the powers first and then multiply. And so that messes up some people. So one of my recommendations has always been to do this. Keep yourself organized. Terms are separated by addition. So there's my first term. And I think to myself, okay, I need 1 times 3 to the 5th. Well, normally I wouldn't punch the 1 in, but for an example here, we'll do 1 times 3 to the 5th, and we'll just let the calculator follow the order of operations and give us our 243. So that would be 243x to the 5th. Then I do this. I put a light line over the top of it to remind myself that I am done with that term. And now I can move on to the next one. You don't want to scribble it because I need to see it when I'm reading the papers. Minus. Again, in your head, you could do 3 to the 4th is 81 and do 5 times 81 times 2. You could do that. But if you don't want to, or you're thinking, I'm going to risk an error if I do that, I'm just going to punch in 5 times 3 to the 4th times 2. I get 810. X to the 4th. For this one? Yeah, the first term is always positive, Ashley. So this very first one, yeah, if that drives you bonkers, put the plus there, you know. When we simplify it, it won't need to be there. All right, now I can cross this one off because this is done. Go to the next term. And that again was my plus that the smartboard didn't like because it ran off the board. So we can hand it over to the calculator and say 10 times 3 to the 3rd times 2 squared. 1080. X to the 3rd. One line through it. Minus. Next box. 10 times 3 squared. Times 2 to the 3rd. Whoops. There we go. 720 x squared. Next box. Plus, now we need 5 times 3 to the 1st is just 3, so 5 times 3 times 2 to the 4th. 240. X minus all 1 times 2 to the 5th is just 2 to the 5th, which is 32. But you can certainly use your calculator for that part as well. So we see we've got positive, negative, positive, negative, positive, negative, all there. And we also see that our x's are in descending order. They're going down. 5, 4, 3, 2, 1, 0. Now, it could be that we'll have variables not only in the first position for A, but we might also have variables in the back position for Y. And that's the one step that just makes it a little more challenging. So you have a lot of stuff that you have to keep track of at one time. But the formula itself stays the same. A's, high to low. B's, low to high. And then go after the signs. So let's look at this one. Although, you know what? I want your 43210 right now. That was a pretty tough one you just did. How do you feel? 43210 is about our objective of expanding. Okay, I still see some 2s. So we'll do this one together, but I'm going to ask you guys to do more. So we have 2x minus 3 being raised to the 4th power. So what stands as our A in that? Sammy, Sammy, what are we using for A? What should we use for B? Zach. Again, you could argue -3, but like I said, it just makes a little bit more of a mess of your powers when you do that. All right, then we need to know what we should start with here. So, after Jackson finishes yarning, how would you start it, Jackson? We've got this as our A term and this as our B term. Again, if I can write down 2x to the 0, but you know what's there. Bailey, we've got our A's from high to low. What do I do now? A's low to high. So my 3 to the 0, I don't even want to write that down because that's going to be a 1. 3 to the first. I'll put my color outside. 3 to the second. 3 to the third, but don't forget your 3 to the fourth. We've got our A's and our B's. And Jordan, what's left here? So how do we know what to pick over here? So we've got a fourth power, row 0, 1, 2, 3, 4. 1, 4, 6, 4, 1. Almost done. One little piece to go. Maddie, what are this? So this one should oscillate? Whoa. Yeah, this one should oscillate. We have a minus up here, so it'll be positive, negative, positive, negative, positive. Next step. I need to know what's in that black box up there when it's all simplified. Logan, what's that going to give me when I simplify this? 2 to the fourth. 16.
16, yeah.
What else?
X.
2 to the go on. Minus. Give everybody a second here to punch this in if you need to. Dylan, you look like you're writing something down. What did you get for that one? Me too. We're going to go after the next box. So are you done back there with that box? Jessica, you're looking done. What'd you get for that next one? 116x squared. Next one, we're going to have subtraction. for the H? Did you get a number yet for that next term? One more to go. Rachel, you finished.
81.
There it is. So, after that one now, I had you do a little bit more on your own. 4, 3, 2, 1, 0. But how do you think it's going? Okay, so mostly 3s and 4s. That is good. So now I need to give you like 90 of these for practice, right? No.
10 of them.
There are more patterns within the patterns here. That's the cool thing about Pascal's stuff. If you go through and look at each of these individual boxes that we had, the powers for these will always add up to the original power. Here we have a 4. There's no other powers. That's 4. Here's a 3 plus a 1, which gives you 4. Here's a 2 plus a 2, which gives you 4. There's patterns within patterns of all of this that are useful. But let me get you a few of these. Go through. Lots. That'll be some good practice. Hopefully it'll stick. Yeah, this will be useful when we start talking about combinatorics. Also very useful. Often what they'll do on the ACTs is they'll say, in the binomial expansion of 3a plus 7b to the 8th, what is the 6th term? It just went to 1. There's a 1 all of them. And we will learn how to do that too, so we don't have to do the whole thing and waste our time on a lot of terms that we don't need. But this is a really good start with that. I gave you 4 of those, just finding the specified terms in the homework. You could go ahead and expand out the whole thing if you want to, or you can try to look at the patterns and see how to get that. We'll talk a little bit more about that tomorrow. So our short Tuesday schedule, I would have liked to have gotten that in with you today. Have a great Tuesday afternoon, everybody. See, Jackson, that wasn't hard. It's just a lot to keep track of. Oh, Logan, is this your jacket?
Oh, yeah, thanks. I always.
It's supposed to be getting colder outside. Is it? Is it? Oh, man,
It's
it was
so
the
cold.
sun.
The roads are better though, so that's good.
Okay.
I almost spun out yesterday with my sister in the car and she was freaking out. She started crying. It's like, we're fine.
Oh, no. How old is she?
She's 14.
Oh!
So
Well,
it's like,
she's scared. That's good. When she drives, she'll know to watch out.
back out of that.
That sounds a lot like my sister. She's 19.
Gets a little worked up, huh?
Yeah.
Yeah, yeah. It is. It's a mess out there. Bye-bye.
She's literally ignoring me like. See me sit here.
Have a good one, Joe.
Yeah.
How are you? Oh, rats.